Good morning. Good morning once again. Welcome to our virtual lecture. Today we are going to start chapter 8. I believe there was some section in chapter 7 which I would like you to read on your own. I know it's pretty straightforward sections remaining. This has to do with electron configuration, which we covered in details previously. The remainder of chapter 7 you can read on your own because of what I intend to cover by the end of this course. It's crucial for those who plan to take Chem 2, in particular chapter 10, where we're going to talk about the Car's laws. You need to understand Car's law for Chem 2 lab. All right. So without wasting my time, continue studying, continue reviewing. I was impressed by your performance in the just concluded midterm 2 exam. Hope you'll do well also in the remaining quizzes and midterm exam. We're going to talk more about that. So let's get started right away with our lecture on chapter 8. I would like to share my screen so that we are all on the same page. Let me share my screen and minimize that and pull the slides. You can use the chat feature as usual. If you have any question, just shoot me on the chat feature on Zoom. All right. Chapter 8, basic chemical bonding. Some others, they put together chapter 8 and chapter 9. Chapter 8 and chapter 9, they are basically on chemical bonding. And chemical bonding or chemical bond in chemistry is defined as, let's just get started by defining what is a chemical bond. All right. Chemical bond is defined as strong, all right, strong electrostatic force. This is force of attraction, all right, attraction between, all right, two or more atoms. That's simply the definition of chemical bond. You are asked what a chemical bond is. It's just a strong electrostatic force of attraction between two or more atoms. That is simple definition of a chemical bond, and there are 3 types of bonds. We're gonna talk about that, but before that, here is the roadmap on what we will cover in chapter 8. One, we're gonna look at the Lewis symbols and the octet rule. I'm gonna talk in details about that in 8.2. Ionic bonding, covalent bonding, 8.3, polarity and electronegativity is a trend on the periodic table. 8.5, we look at how to draw the Lewis structures of atoms and resonance structures, which is basically this structures of the same compounds having different position of either double bond or triple bond. We're gonna talk about those type of bonds. We look at the exception of octet rule in towards the end of the chapter and wind up from there, chapter 8, move on to 9. Let's see, there are 3 types of bonding. I've just defined what a chemical bond is. All right, chemical bond in chemistry is defined as a strong electrostatic force of attraction between 2 or more atoms. And there are 3 of them. You should be aware, you should know, you should have in your fingertips. One, we have what we call the ionic bonding, and ionic bonding is force of attraction between two ions. You should know what ions are, positive or negative. Remember, cations and anions, all right? Negatively charged and positively charged. For example, sodium, which is positively charged, and chlorine, negatively charged. The force of attraction between these two ions constitute what we call ionic bonding. This is cation, positively charged, and this is anion, which is what? Which is negatively charged, negatively charged. The ions, you know how you can predict. We're going to look at how to predict ionic charge for ions using the periodic table. We saw this in chapter 2. It's going to come back again in ionic compounds. Now we have covalent bond. Here is ionic bond formed between metal, you know where metals are on the periodic table, plus non-metal. So it's not only sodium and chlorine. You can have any non-metal, all right? You can have any metal. By looking at the chemical formula, you can say, oh, this has ionic bond. Now, covalent bond, on the other side, covalent bond, all right, has, this one is made up of two non-metals sharing electrons. We're gonna talk about the sharing later on, but by looking at the chemical formula of a compound, you can tell whether it has covalent bond. These are non-metal, all right, non-metal plus non-metal. This is how I can tell whether a compound has a covalent bond. This is sharing of electron. You see on my whiteboard, there are two electrons being shared here by these two hydrogen atoms. The diagram here just shows the three types of bonds. So far, you've seen the covalent bond, sharing of electron, and ionic bond formed by cations and anions, negatively charged and positively charged particles. And then lastly is the ionic metallic bond. Metallic bond is a bond where atoms float in a sea of electron, all right? So it could be electrons, and we can have an atom there, an atom there, an atom there. You see, these blue spheres on my whiteboard represent atoms. So if this is an atom right here, this is an atom, all right? And these are electrons. In metallic, all right, in metallic bond, atoms float around in a sea of electrons. You see what we have in parentheses, in quotes. Electrons, they don't, they are not shared or they are not transferred between atoms in metallic bonding. So as we talk of in chapter 8, know that there are three types of bonds: covalent, ionic bond, and metallic bond. You should be able to distinguish between the two types of bonds. You should be able to distinguish between the three, not the two, the three types of bond. We will be looking at compounds which have these three types of bonds, ionic and covalent. Any question on the three types? With the periodic table, you should be able to, state whether a compound has covalent, metallic, or ionic. Now let's move on to 8.1, Lewis symbol and the octet rule. Who was Lewis, by the way? Green, Newton, Lewis, GN. GN stand for Green, Newton, Lewis. He was an American chemist born in the state of Massachusetts, and he's credited for different theories and principles in chemistry. One of them is what you already know, a photon. We talked about a photon a while back in chapter 5. He is the person who proposed that it's a photon. And in this section, covalent bond is credited for the discovery of the covalent bond. He theorized that when atoms react to form bonds, they use their valence electrons. And you know what valence electrons are, right? Valence electrons. These are electrons, all right, electrons in the outermost shell, most shell, or electrons in the highest energy level, or highest principal energy level. We have to write electron configuration of an element, and then you should be able to see the valence electrons. Valence electrons are electrons in the highest energy level. This is L, the last one right there. And these electrons are involved, or they are used in chemical bonding. If I have, say, sodium if this is sodium, 2 electrons and 8 electrons here. For sodium, you have 8 electrons, right? And the outermost shell has 1 electron. This is the valence electron. Valence electron. In relation to Lewis and the octet rule, all right, when main group elements react, they make use of their valence electron in chemical bonding, and it is very easy to figure it out, the number of valence electron for main group element. If you look at the periodic table, or portion of the periodic table right here, there is group 1A, group 2A, group 3A, 4A, 5A, 6A, 7A, and 8A. The group number corresponds to valence electron. So it's not a big deal that you need to memorize how many valence electrons are in organ. So anything on group 8 except helium has 8 valence electrons. Now, group number corresponds to the valence electron. Take note of what happened when, for main group elements, metal tend to lose and non-metal tend to gain electron to end up with 8. So in chemical reaction, in the process of forming chemical bonds, they either lose, or they either gain, or share. In the long run, they end up with 8 electrons, except this one, because, you know, if I don't say, it's just gonna be a problem down the line, except hydrogen do not end up with 8 electrons when it form a chemical bond. It ends with 2 just like helium in group A. So let's see the dot symbol for elements. Dot symbol for element. Let me just show you dot symbol. I mean to say dot symbol for atoms or maybe elements is basically the chemical symbol and the dot around it. For example, lithium is in group 1. I'll have only 1 dot around it, or just anyway you can put that. Aluminum is in group 3A, and you just have to put 3 dots around it. I know you know this, 1, 2, 3. This is aluminum. When it gets to carbon, which is in group 4A, this has 4 dots around it. It's important to note that you do not pair them until they are singly distributed around the chemical symbol, and the maximum you can go with singlet distribution is 4. Nitrogen now, which is in group 5, you go around 1, 2, 3, 4, 5. So you see there are 3 unpaired dots around the chemical symbol for nitrogen. For oxygen, all right, 1, 2, 3, 4, 5, and then 6. You see there are 2 unpaired electrons around oxygen. When I get to fluorine, all right, look at fluorine, 1, 2, 3, 4, 5, and 6, and 7. There is only 1 unshared electron in dot symbol for fluorine. Any group 8 except helium has a paired 1, 2, 3, 4, 5, 6, 7, 8. So those are the dot symbol for few elements on the periodic table, and I'm using the group number. In the exam, all right, in the quiz, given the periodic table, you should be able to either identify the symbol, you know, it shouldn't be, pay attention to the pairing. With that, let's see, on the PowerPoint slide, are all these Lewis symbols for chlorine atom? Are all these correct? A, yes, all of them. B, no, the first 2 are different Lewis structures because of the different placement of unpaired electrons. C, which one is the appropriate answer for the PowerPoint slide on your right side of the screen? How will you respond to a question similar to what you see here? Because you need to understand the concept of dot structures for symbols before we move on to a more advanced dot structures for molecules. We need to understand the first atoms. Which one is wrong? Which one is correct? Are all these correct for? Are all that correct for? Use the chat feature to look at. Look like somebody is not responding. Please, can somebody help us move forward? C, yes, correct. David, you're right, C. No, all of them are not, because the Lewis structure on the right, this one, has 6. We know chlorine is in group 7, and we expect to have 7 dots around it. And if you count here, we have only 6. So the correct answer is C. That should be easy for conceptual question in a quiz or exam. Now, here is another question on the symbol. You should have your periodic table ready. And, you know, there are some terms they expect you to remember. Some concept we looked at earlier on, you are expected to remember. They are dash, all right? They are dash paired and dash unpaired electrons in the Lewis symbol of fluorine molecule. I'll help you out with this. This is the catch lines right here, molecule. This is an atom right here. And this is what? This is a molecule. It's diatomic. So if I'm looking at this will be 1, 2, 3, 4, 5, 6, 7 for fluorine. But for a molecule, we're gonna come back to this Lewis structure for molecules, and I'll walk you through on how to end up with this. So you expect to have 1, 2, 3, 4, 5, 6. All right, all of them. All the 2 atoms here ends up with 8 electrons. The lines here stand for single bond, all right? 2 electrons here being shared, and the dots here represent unshared, all right? Unshared. We're gonna talk about the lone pairs later on. For these questions, you are expected to know the difference between an atom and a molecule. The correct answer for this is C, is to help you with this problem on fluorine molecules. Hydrogen molecule, just to give you what are the atomic, there are 7 of them. Oxygen molecule, chlorine molecule, bromine molecule is PR2 and I2 molecule, hydrogen. There are 7 of them, 1, 2, 3, 4, 5, 6. Which one am I missing here? Chlorine, iodine, oxygen. All right, there is nitrogen gas. I forgot about that. This is also diatomic molecules. We will come back to the structures of molecules. So back to ionic bonding. Ionic bonding are formed as a result of transfer of electrons from a metal to a non-metal. Ionic bonding is formed, all right, ionic bonding. Electron, this is formed as a result of electron transfer from metal to non-metal. There is electron transfer. In case of sodium chloride, an electron is transferred from what? From metal to a non-metal. So for group A, this electron transfer. Now, the number of electrons transferred corresponds to the group number. All group 1 will lose 1 electron, all group 2 will lose 2 electrons, and so forth. Group 3, aluminum, will transfer 3 electrons. And they are all exothermic, which means giving away heat. So for this type of bond, how will you know that a compound has ionic bonding in them? If it consists of a metal and a non-metal in there, and then you know the type of bond there is ionic bonding. It's not only limited to chlorine and fluorine. And remember, it is formed as a result of electron transfer from metal to non-metal. It's not from non-metal to metal. It's one-way traffic, metal to non-metal. So recall from our trend in chapter 7, ionization energy means the amount of energy required to remove an electron from an atom in gaseous state. So metals tend to have low ionization energy and they give up their valence electrons. Adding electron to a non-metal give away energy, and we call that electron affinity, and this leads to what we call ionic bond. All right, ionic bond. If you look at the transfer, this arrow means transfer of electron to end up with a cation and an ion. Take note of how the Lewis structure. This is, by the way, this is the Lewis structure for. This is the Lewis structure for what? For sodium ion. All anions negatively charged, when they gain electrons, you use parentheses to indicate that there is an overall charge of negative when indicating that extra electron has been added to the atom. If it is oxygen, you're just gonna have -2. Not like that, but this is what I want to say, that for oxygen or oxide, for nitride, that means it has gained 3 electrons. And by the way, this is 1, 2, 3, 4, 5, 6, 7, 8. It has gained. For anions, they have an overall charge. In parentheses, you indicate that to indicate formation of anion negatively charged and cation positively charged. So you could have Ca2 positive, and this is cation, which means it has lost 2 electrons. And this is the Lewis structure. You'll have expected neutral to have this. Remember the neutral calcium? This is neutral. That means it has not lost any of the valence electron, 2 valence electron. Something I need to bring to your attention, how you write the dot structure for anions, that means negatively charged. So having said that, knowing what constitute ionic compound, metal and a non-metal, you also need to know the properties of metals, I mean ionic compounds, not metals, ionic compounds. They are brittle, all right? You know what brittle means? That it can easily shatter into pieces. If we use an hammer, for example, maybe you have experiences, if you crush a table salt, a crystal of table salt, all right, it will shatter into powder, or split it into 2. For example, it's a huge. The reason behind that is, if the crystal structure of sodium chloride look like this, all right, and I do have another one right here, maybe just to give you an idea of what happened when you crush a table salt. Why we say brittle is, if this is positive, this is positive, this is negative, this is positive right here, positive, and this is negative, negative. It is, you are aligning, you are dislodging this arrangement here. You are dislodging this arrangement in such a way that negative and negative will be together, and positive and positive will be together, like that. And we know from classical physics that negative and negative don't like each other. It means I'm just dislodging. When I use a hammer, the negative and negative will be aligned, positive and positive will align, and the crystal will break apart. It will shatter. That is what takes place at atomic level. Otherwise, just neutral, or at the crystal structure is alternating negative and positive, negative, positive, negative, positive. With that spread. They have high melting point. I think the melting point of sodium chloride is around 800, around 800 degrees Celsius. They all have high melting point. Crystalline and have a long, smooth lines. Well, I will not go in details into the Born-Haber cycle and how to calculate the lattice energy of sodium chloride, but I just want to mention what is lattice energy. Lattice energy is the amount of energy required to break apart a crystal into its respective ions. For example, here is sodium chloride. It is solid, it's crystal structure. The amount of energy required to split sodium from chlorine into respective sodium and chlorine in gaseous state is what we call the lattice energy. The lattice energy, we talked about that. This is what the definition is. You have to know what it is. It's the energy required to completely separate 1 mole. And the word mole is because it is given in units of kilojoules per mole. That means if I have Avogadro number of this formula unit, one of them is formula unit. That is 1 sodium and 1 chlorine put together. I end up with sodium chloride formula unit. If I have Avogadro of this, 6.022 times 10 raised to 23 formula units, all right, of NaCl, the amount of energy required to split this into respective atom is what we call the lattice energy for sodium chloride, and it varies from compound to compound. Lattice energy is given in kilojoules per mole. Kilojoules per mole. Understand that what this means. What has positive 788 kilojoules per mole in this reaction? Is it exothermic or endothermic? What has delta H lattice mean in this equation? Is it exothermic or endothermic? Let's wrap around our mind what this means. It's gonna come back again. What does positive mean? Endothermic, thank you, David. That means we need the energy to supply, like energy has to come in. You see this? I have to have some energy right there to get into, to split it into 2. It's endothermic, so negative exothermic, and all lattice energy, they are positive, they are positive. So here are just, the lattice energy for different ionic compounds, and I want us to learn something out of this table 8.1. Table 8.1, there is a message lying here. which I want to, you know, point out to you, and having an understanding that atomic radius, all right, atomic radius increases you go down, as you go down a group, because you will have more what? You need more shell. You need more shell, all right? Now, as you go across, it's getting small and small and small and small and small and small and small. That is the trend on atomic radius, atomic radius. You need this understanding to understand what is going on the trend on lattice energy. Let's see. If I have a 1 meter stick, all right, you know what a meter stick, you know, you don't know where you are right now, but just visualize a meter stick versus my, you know, stylus pen. Look at my stylus pen. I don't know if you can see from where you are. This is my stylus pen. And I have on one hand, I have a meter ruler. Which one will be much easier to break? Is it 1 meter stick or the stylus pen? Just respond using the chat feature, please. Will it be much easier for you to break the stylus pen or much easier to break a meter? It doesn't really matter which method you use. The meter stick, thank you, Stephen. So we are on the same page now. If you look at the trend here, even though we have lithium, 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 look at the first 3 compounds on the table, lithium, lithium, lithium. So ionic radius of lithium will not really change. I'm just gonna use this right here. Hopefully I'm just gonna have a constant radius, assuming that that is lithium. And because of that, I'm just gonna try and have same radius. I'm trying to get the same radius. This is lithium, lithium, but look at the second element or atom in the compound. That means if we go across the periodic table, atomic radius get, you know, smaller and smaller. So I'll expect atomic radius of say here, let me use fluorine to be like that. And then when I go down chlorine, it is getting bigger, all right? And then when I go down here, it is getting bigger and bigger and bigger, all right? So you look at this element right here in terms of what I have on my whiteboard. And using the analogy of, you know, meter stick, you could, it's very, you know, you can handle, you can use your knee to break, you can use your foot to hold it and break it apart. So the longer it is easier to break apart. So in the same analogy, if you use that approach, you will see why lithium fluoride has high lattice energy. It is so hard to split apart because of, you know, not necessarily the, you know, the small size, but because of the nucleus and you know, they tend to be strong force. They're so close that it is so hard to do it. It is so hard to break it apart, and that explains this trend right here. You see this? It is getting larger. Chlorine right here. This is chlorine. This is iodine. If we add something below on group 7, it will even get bigger and bigger. So this is what I will use in terms of, you know, the trend on the periodic table. And that explains this trend you see here. In the exam, I may give you 3, look, I may give you 3 compounds or ionic compound and say, arrange this according to increase in lattice energy. And I don't give you, you know, I don't give you the values here for you to really see it, but with an understanding or using this analogy, you should be able to, use the atomic radius. I've used atomic radius and I see it's working. That will tell you that it is, which one will have high lattice energy and small lattice energy. If you look at this also, sodium, 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 not a big deal. But when you look at fluorine, chlorine, we are going down group 7. And the lattice energy is decreasing, that the atom is getting larger and larger. And the nucleus will be much far apart because this second atom is or has large atomic radius. So if I look at all of them, it follows the same trend. Magnesium, calcium, getting bigger and bigger. Magnesium is small in atomic radius. Calcium is below strontium. You see how it's getting bigger? That is what you need to pay attention when it comes to lattice energy. When it comes to lattice energy, question could be, how do you arrange this according to increase in lattice energy or decrease in lattice energy? Using the trend on the periodic table, it should be easier for you to answer such questions. Any question? Somebody who is not here may, it's gonna be a challenge because I may pick other elements other than what you see on the periodic table, and that is the trend. So when you read, understand that that is what is going on. So you should understand now why this trend is increase in the cation radius. All right, is inversely proportional to lattice energy. The larger the ionic radius, the smaller or the less the ionic. Now, as this increase the radius, it's the same thing for anions and for cations. It follows the same trend. So if I give you other elements other than that, you should be able to state the trend in lattice energy, Now, with that, you should have your periodic table in front of you. Place the following in order of decreasing magnitude of lattice energy. How are you going to answer that? Which one is the correct answer? There is sodium fluoride. You can use elimination method. And guess which one is correct. You can use elimination method. Remember, this has to do with, yes, correct. Aaron, you got it right, because if I look at the cation first, the smallest among the cations, you see sodium. If I have the sodium, group 1 sodium is at the top right there, followed by potassium somewhere there, and then rubidium. This is the arrangement of group what? Group 1. And then there is fluorine. There is fluorine, chlorine, and bromine, like that. Yeah. So the smaller it is, the one with the smallest, you see this combination two here should be hard to split. They will be just too close like that. And it should be the first one in decreasing. It will have high lattice energy. And if I use this as the one with the highest, using elimination method, I see that B is the only one. This will have, rubidium, the largest right here, should be the last. And if I look at the last, using elimination method, sodium fluoride should not be before potassium. And otherwise, Using that approach, it's not going to fall. The correct answer is B. And you can mark your periodic table and say which one is smaller, or you can write it down the way I wrote it here, that, okay, let me see cations. It's, as you go down, the cation radius increase. And we know the relationship between cation and the, from here, cations and the lattice energy, as it gets larger and larger and larger, the lattice energy decrease. So that's why we say it's B. Correct answer is B for this. So please read again, understand the trend on. If you look at this, we didn't have to know the values. We didn't have to know the values from the previous table in order to make that conclusion. It's just the general trend, Oh, well, let's move on to electron configuration of ions. I think I did mention this last time. If you know how to write electron configuration for main group elements, and in particular, they are using the long method, it should be well-rounded in 3 anyway. 1s2, you know how you end up with this 1s2, right? 1s2, 1s2, you know what 2 means, 2s2, 2p6, 3s2, 3p6, 4s2, and what, 3d10, please, and then on and on and on, using the 1s2, 1s2. Now, the ions are formed when a neutral compound either loses electron or gain electron. And this loss of electron is not any electron, it's the valence electron in most cases. Valence electron. So if I was to write, all group 1 will lose 1 valence electron. For example, sodium, S, 1s2, 2s2, 2p6, and 3s1. This is sodium with 11 electrons. But sodium cation means we are less by 1 electron, and the 1 electron will be from the outermost shell, 1s2, 2s2, 2p6. You don't see the 3s1 because, it's gone, it's lost, and we end up with that. Main group elements, in this case, a metal will lose the valence electron to 8. So this is group 8. It's just like neon with 10 electrons. Non-metals also gain electron corresponding to how much they need to get to 8. Non-metals, for example, chlorine, this is number 17, 1s2, 2s2, 2p6, 3s2, that is 12. We need 5, so 3p5. It's not going to lose. I know somebody must say, why don't we follow the trend we use in sodium and just say it's going to lose 5? No. Non-metals, look here, gain electrons, and the electron gain corresponds to how much you need to get to 8. For example, here, the highest n value in these two right here, you sum up. Right here, we need 1 more electron because 7 plus, or 7 is obtained from 2 and 2 and 5. So we need one more electron to make the outermost shell just be like a noble gas electron configuration. And this is the ion. This is an ion, anion, negatively charged. And its electron configuration is 1s2, 2s2, 2p6, 3s2, and what is 3p6. We have added electrons to the outermost shell, and the number of electrons is how much you need to get to 8. Group 7 needs 1, group 6 need 2, group 5, all right, need 3, except, you have to be careful with group 5, because in group 5, we have the non-metals at the top, and we have metals at the bottom, bismuth. When you come to group 4 also, there is carbon at the top, and then there are non-metals below it. Lead, for example, will not gain. You gotta be careful on when you are dealing with a metal and a non-metal. Now, transition metal do not follow the octet rule. All right, yes, I used this example before. How do we write electron configuration for transition metals? Example is iron. All right, iron is number 26, which means it has 26 electron, and you'll expect just electron configuration 1s2. Maybe I don't have space for that. Let me write it down here. 1s2, 2s2, 2p6, 10, 3s2, 12, 3p6, 18, and then 4s2, this is 20, and then 3d6 to make it just a neutral ion. But if it is ion 2, like that, ion 2 positive, this is a cation, that means we are less pi2 electrons. And take note of this, that it does not really follow the octet rule, like, okay, it needs to make 8. But the valence electron will go out fast. These are the electrons which will go out fast. So we will write the electron configuration for this as 1s2, 2s2, 2p6, 3s2, 3p6, all right, and then 3d6. You got to know how you write the electron configuration for ions. I could also have this argon, which will take care of 18 electrons up to this point. We have 18, and then just put it 3d6, 3d6. In the exam, you may see a question saying, what is the electron configuration of this? And somebody will give me this one, and that will be wrong. You got to know how to write the electron configuration for ions. The inner or the valence electrons get lost fast for transition metals. Transition metals loses the valence electron fast and then loses the D. So when we come to ion 3, like that, ion 3, this will be 1, or let's just use the shorthand. All right, I'm just gonna use the shorthand, that is argon, which is 18. And if we lose 3 electrons, it's gonna be 3d what? 3d5, because the 4s2 is gone, and 1 electron in the I'm gonna lose 2 here, and then remove 1 electron from here and make it d what? And make it d5. That is the electron configuration of ion 3. Just using an example of ion to show you how valence electrons are removed fast before you lose the 3d necessary to give the ionic charge. Any question on writing electron configuration? You should be able to write the electron configuration of ions using the three methods. For example, here, I can also write here argon. You may see this in exam, and then 1, 2, 3, 4, 5. Remember the D, the 3D, subshell has 5 orbitals, and I'm just gonna have the 5 electrons. 1, 2, 3, 4, 5. They are singlet. They are degenerate, and they just open it. That's another method of writing electron configuration. Now, based on the octet rule, magnesium most likely forms a dash ion. Which ion do you expect to be for magnesium? Is it A? Is it B? Is it C, D, or E? Which one? Aaron, did you say B? Somebody say B? Yes, it is A. David, correct. It is A. It's based on the group number. If you are doubting yourself, or if you don't know the game plan on this, I recommend use periodic table. Don't rely on your memory. These are the kind of things you don't memorize. You know, you cannot memorize all the ionic charges. You know, magnesium is in group 2, and the number of electrons lost corresponds to group number. Therefore, A is correct, Mg2 positive. No, this is wrong. This is wrong. This is wrong. This is wrong. Wrong. So using elimination method, the correct answer is A. The correct answer is A, writing the ionic. Based on the octet rule, phosphorus most likely forms a dash ion. It's the same, you know, approach. You gotta know which group is phosphorus. The challenge is, if you don't know the chemical symbol for phosphorus and you are given the periodic table with only chemical symbol for elements, you know, you may say, what it is? Is it P for potassium? Yes, correct, David. It is B. Yes, phosphorus is in group 5, and 5 needs group 5A needs 3 more electrons to achieve the octet rule. Correct answer is B. Shouldn't be that difficult. Thank you. Shouldn't be that difficult. That marks the end of ionic bonding, and what you need to do, if you just think of it, the concept we just went through it's not new. You know, some of the concept we looked before: electron configuration, how to predict the ionic charges, what octet rule means. All right. Just go back and read again on that. Let's shift gears to covalent bonding. And I explained earlier on what covalent bonding is. It is a bond formed as a result of sharing of electrons between atoms. There is no electron transfer. If you look at the positive and positive, this stands for the nucleus of an atom, all right? And here are the shared electron, which really holds the atoms or the molecule, in this case, together. How it works is, this is what you want to visualize. If this is the nucleus with a positive, and then this is the nucleus with a positive, if this is, all right, if these are the two atoms, this one has an electron, and this one has an electron, which is negatively charged, this is negatively charged. The electron here is pulled by this nucleus, and the electron here is pulled by this nucleus, and in the process, the sharing of electron comes in to hold the two atoms together, sharing of electrons. Is the key thing in covalent bonding. Covalent bonding. Now, in covalent bonding, there's a way of representing these shared electrons. We use a line to represent shared electron. Sharing of electron is shown by a single line, and you start off with the dot symbol for element. For oxygen, for example, hydrogen gas, the dot symbol for each atoms look like this. Each of the hydrogen needs one electron to be like helium, which is group 8. And thus 2 electrons are shared. I can use an X here, so that X and a dot, and each one of them is claiming the 2 electrons right here. These are the what? Shared electron. And we represent that using a line. So moving forward, a line represents shared electron. For chlorine and any other elements, if we have chlorine right here, 1, 2, 3, 4, 5, 6, 7, there is unshared electron right here. If I have another chlorine here, 1, 2, 3, 4, 5, 6, and then there is unshared electron right there. The 2 atoms will share. And then I have chlorine here with the electrons right there. So each one of them is sharing the 2 electrons. These are the shared electrons, and we represent that Cl like that. The 2 here, we call these unshared electrons, unshared electrons. Paint a picture of what how electrons are shared and how the covalent bond are formed in covalent compound or molecular compound. To state the number, there is a way you can state the number of covalent bond an element can form. Number of bonds formed by nonmetals corresponds to unshared electrons. When you draw the dot symbol for an element, the number of bonds you expect for that element to form corresponds to unshared. Chlorine, for example, has 1, 2, 3, 4, 5, 6, 7. So there is unshared. So this will form 1 bond. If I have nitrogen, let's see nitrogen. 1, 2, 3, 4, 5. It is in group 5. Here are the unpaired electron, and we expect nitrogen to form 3 covalent bonds corresponding to unshared electron. If you look at fluorine, fluorine has 1, 2, 3, 4, 5, 6, 7. There is unshared electron on fluorine, and it will form 1 covalent bond. For carbon, all right, 1, 2, 3, 4. We expect carbon to form 4 covalent bonds. So these are not the only these are not the only elements, you know, you need to learn or to memorize to state the number of bonds. First, you got to draw the dot symbol for that element, and you should be able to see how many covalent bond you expect to form. It corresponds to the lone and unpaired electrons around the chemical symbol. Having said that, we have two classes of electrons. One is the lone pairs and the bonding pairs. Here, these on my whiteboard, these are the bonding pairs. Remember, a pair has two. They are located, all right, on one atom. Lone pairs are located on one atom. These are the lone pairs. The first chlorine atom here, 1, 2, 3, it has 3 lone pairs, bonding pairs. So in Lewis structures, note the 2 types of electrons. I've seen questions tailored around this slide here that how many bonding pairs are in chlorine molecule? We have 1 bonding pair. How many lone pairs in chlorine molecule? We have 1, 2, 3, 4, 5, 6. We have 6 lone pairs. We have 1 bonding pair. If I look at this example here, in water molecule, we have 1, 2 bonding pairs and 1, 2 lone pairs. In ammonia, we have 1, 2, 3 bonding pairs and 1 lone pairs. Lone pairs, all right, lone pairs, they are located outside or they're just in one atom. You need to know that so that when we look at that, it's gonna be easier for you to look at bonding pairs and bonding pairs. Lone pairs and bonding pairs. Let's look at the 3 types of bonds you need to understand, because we will use that down the line. Single bond here, we call a line a single bond. This is called single. This is single what? I meant to say single bond, and it has 2 electrons, which is one pair. You know what a pair is? It means 2. Double bond is 2 lines, and this is called double bond, and 2 pairs. And this is called triple bond, all right? And it has 3 pairs of electrons. This has 2 electrons. This has 4 electrons, and this has 6 electrons. You need to know the difference between the multiple bonds. These are multiple right here. These are multiple, double, or triple. You look at 3 lines, 2 lines, they represent double bond, triple bond. Good to know that. Any question on multiple bond? What we say, double bond, triple bond? I know you know this. Let's move to 8.4. There is a term here I want to define before we move further on 8.4, electronegativity. All right, is the ability of this term here, electronegativity, This is the ability of an atom to attract electrons towards what? Towards itself in a covalent, that means share, covalent bond. This is how you define electronegativity. It is the ability of an atom to attract shared electron toward itself in a covalent bond. And the trend on the periodic table, we'll see it much later, it's just gonna be a minute. The trend on the periodic table, if this is the periodic table, and going that way, this increases. And then it decreases as you go down a group. And when there is an equal sharing of electron, when there is an equal sharing of an electron in a covalent bond, for example, H and fluorine here, there is an equal sharing of electrons because fluorine is more electronegative. So the electrons we have right here will spend more time around fluorine because fluorine is more electronegative. We say that this bond is polar. We say this is polar what? Polar bond, and the molecule is said to be polar. Polarity is a measure how an equal electrons in a covalent bond are shared. Non-polar covalent are electrons shared equally. For example, here hydrogen will share equally. They have the same electron. We say this is non-polar bond, because there is equal sharing. Whereas HCl, this is polar covalent bond because of an equal sharing. Polar covalent because of unequal sharing. Why do we say unequal sharing? It's because of this, because of the property of element on the periodic table we call electronegativity. When there is unequal sharing, it leads to what we call bond polarity, and polar when there is unequal sharing, non-polar when there is equal sharing. Sometimes chemists use electrostatic potential mark to show portion of the molecules with high electron density and the region where there is low electron density. If you look at this diagram here, fluorine is more electronegative and it tends to pull electron toward itself. So this portion of the molecule has or have high electron density compared to the blue painted portion of the molecule. Is electron poor side of the molecule. Chemists use that rule of thumb. I don't know why, who picked up that, but as far as we are concerned, sometimes they use that to represent polar covalent bond, Let's look at the periodic table and how the trend changes. I gave you this earlier on. This is the periodic table. You don't need to memorize these numbers, by the way. You'll be given if need be. All right. What I want you to take note of is the trend on the electronegativity as you move from left of the periodic tables towards right. It's increasing. And as you go up a group, it increases. Mine is just, pointing down and decrease. You gotta be careful on where the arrows are pointing. My exam question could be, as you go up a group, how is the trend on electronegativity? And somebody will say, oh, I remember him saying it decreases. The arrow was, no, you have to see where they are on the PowerPoint slide. It's just pointing up. On my whiteboard, it's pointing down. It conveys the same message. So as you go down a group, it decreases. As you go up a group, it increases, and vice versa. The most electronegative element on the periodic table is fluorine with an electronegativity value of 4.0, and the least is cesium with an electronegativity value of 0.7. There will be a time where we'll use these values, but we don't need to know what is it for now. Now, let's see. A question similar to what you see on the screen is, which one do you expect to have the lowest electronegativity value? Don't just say, oh, am I gonna do that? With my periodic table, I'll just have like a scratch paper similar to what I do have here and say, let me just, you can mark the periodic table and say, let me position, knowing that this is increasing and knowing that this is decreasing. So I'm just gonna label this and say silicon is somewhere there. And then nitrogen is a little bit farther left on silicon and still above. Yeah, and still above silicon, that's nitrogen. And then gallium is somewhere here. And then cadmium is all the way right here. This, I don't know where it is, but you can see now which one is the lowest electronegativity value. From my illustration, from the diagram, you can easily see that the lowest electronegativity value. Cadmium, CD, this is cadmium, will be the one with the least. It is down and it is far to the right. I don't need to have those values to make a conclusion on this question. You have to eyeball and say, all right, if this is my periodic table, where will I put it? All you have to know is the general trend on electronegativity and say, all right, moving from left to right, it's increasing, and moving from top to bottom on a group, it decrease, and or going up, it increase, and then you just eyeball, and it's just gonna be clear here that the one with the least or the lowest electronegativity value will be cadmium, without necessarily trying to find the values and say, how will I know, without having those electronegativity values. So next time, it could be arranging elements according to increase in electronegativity, or according to decrease in electronegativity, or which one has the highest electronegativity, and so forth. Right? It will just be straightforward. No one will give you, something which is hard to really figure it out. No one will ask you how to really figure it out. Now, electronegativity, actually, as I explained, when there is an equal sharing of electron in a covalent bond, it leads to what we call, dipole moment, which represent the displacement of electron. The portion which is electron poor is indicated with a positive N, where the arrow indicates the region where electrons are being displaced to. Partially positive, this is a Greek symbol. Delta positive means electron poor region of the molecule. I normally use, what I already know to really understand this thing. Electrons are negatively charged, and it makes sense to use a delta negative to show that we have high electron density on a more electronegative element. So when there is unequal sharing, if you see this, then you can tell which one has electronegative. Let's see, which one of the following molecules contain the most polar bond? The most polar bond. Use the periodic table and state which one will have highest or most polar bond. Which one has the most high polar bond? I need some help here. Use the periodic table. Remember the general trend on the periodic table. The more electronegative elements have the highest power to pull electrons toward itself, and it will lead to the most polar. How will you figure it out is? You can use elimination method and say which one has or which one will be, or which among these compound has an atom with the highest electronegativity value. Which one has the highest electronegativity value? Fluorine, chlorine? Yes, hey, David, that's correct. If you look at the table, fluorine is the most electronegative and cesium is the least electronegative. So anywhere I see fluorine, that means it will have, fluorine will have high power to pull electron toward itself than any of the elements in these other compounds. Therefore, consequently, this will have the most polar bonds because of an equal sharing without necessarily, looking at how they are arranged on the periodic table. We can also use electronegativity values to state or to determine whether the bond is more electronegative. Apart from just looking at the position, you can do the calculation on, all right, the difference between electronegativity values to tell which one is more polar. For example, here, hydrofluoric, hydrochloric, hydrobromic, and hydroiodic, the bond length and electronegativity values. You see electronegativity values, the difference. And how that works is, you need to know that in hydrogen fluoride, you'll be given these values. How this difference, we call this change in En, in electronegativity. Change in electronegativity. This value right here, I'll give you, or you'll be given in an exam, maybe this right here. Let's see, go back here. For fluorine, it is 4.5 or 4.0. And if I look at hydrogen, this is 2.1. 2.1. 2.1. With that, all right, to find the electronegativity value, or difference, sorry, is 4.0 minus 2.1. And there is, this is the change in electronegativity value is 1.9. It is the, not a smaller value. The higher value minus the smaller value gives you change in electronegativity. So these values you see here is obtained from the values. If need be, you will be given for different atoms in a molecule in order to calculate the electronegativity values. If you look at the bond length and dipole moment, correlates to change in electronegativity. And there is a benchmark here, change in electronegativity. 0 to 0.4 the bond is, we say non-polar. That means there's equal sharing of electrons. If change in electronegativity is 0.5 to 1.9, the bond is polar covalent bond. And 2.0 should be here, greater or equals to 2.0. That means 2 or greater than 2.0. The bond is classified as ionic bond. We use tools to classify. The benchmark you see here in electronegativity values tells you whether the bond is ionic, covalent, or non-polar. Non-polar 0.0 to 0.4, 0.5 to 1.9, polar covalent bond, this is bond, and non-polar bond. It's gonna give you the electronegativity values. Let's see, given the electronegativity values below, which covalent single bond is polar? You know, this question here, somebody will say, I thought, you know, all of them should be covalent bond. With the initial definition of a covalent bond, a bond between two nonmetals, all of them, they are nonmetals. If you look at this, all of them, they are nonmetals. So we can't say that they are not covalent bond. And all of them, they are single bond, you know. It's even confusing that I think all of them are single bonds. What am I looking for? It is with understanding of this table right here that when we do the difference, let's say A is 1.4 or 2.5 minus 2.1. 2.5 minus so A, this is 0.4, B is 3.0 minus 2.1. I see 0.9, 3.5 minus 2.1. C is 1.4. D is 2.5 minus 3.5 minus 2.5. This is 1.0, and then E, the electronegativity. What I'm doing here is change in electronegativity values. Change in electronegativity values. And lastly, nitrogen and oxygen. So this is 0.5. The question here is now, given the electronegativities below, which covalent bond is polar? Most polar. You look at the C, this has the highest value. The most polar in this case will be based on the highest electronegativity polar bond, single bond with the highest difference in electronegativity values. Highest in electronegativity values tells you whether the bond is most polar. Other than that, if you look at all of them, they are covalent bonds, they are single bonds, all right? Change in electronegativity values helps you in determining which one is the most polar. That means there is greater displacement of electrons, I want to stop here today, and next on Thursday, we will pick up from here, all right? If there is no question, any question, if there is no question, I will stop sharing my screen and the lecture session we will meet on Thursday. Thank you. Please continue reading on chapter 8. And I'll see you on Thursday. The lecture is ending. Thank you for tuning in. See you on Thursday. Be safe, stay healthy.